Welcome to the Developer Journal. We are witnessing a fundamental shift as artificial intelligence evolves from passive experimental models into active production participants. This transition is forcing engineers to completely rethink how we handle foundational vision systems and manage complex context strategies across the entire enterprise cloud governance ecosystem today. Today, we explore how Google DeepMind is challenging existing vision standards like Segment Anything Model 3 with their instruction-tuned models. We also examine the dangerous rise of prototype pollution within autonomous coding tools and why so many sophisticated agentic systems fall apart the moment they leave the safety of development.
That specific leap from a simple sandbox to a live environment exposes every single crack in the logic. I am digging into Microsoft's OpenMementos to see if trace analysis can truly prevent our large language models from drowning in their own data, while maintaining strict governance over every autonomous action taken.
Stability remains the ultimate goal for every architect we follow. From high-performance vision benchmarks to the complex governance needed for autonomous enterprise deployments, we are mapping the new frontier of software engineering. We are starting today with the breakthrough in visual understanding that has everyone at Google DeepMind talking right now. Google DeepMind is fundamentally changing the standard engineering playbook by treating visual perception as a generative image task rather than a traditional classification problem, which allows their new model to reach 0.793 generalized intersection over union on the reasoning segmentation benchmark, without requiring any specialized task-specific decoder heads at all. By streamlining the vision architecture this way, the research team is proving that generative pre-training can act as a universal foundational learner for computer vision in a way that mirrors how large language models developed an emergent understanding of text, suggesting we might finally be simplifying the complex stack needed for enterprise artificial intelligence. The real-world business impact is clear when you see this system outperform the specialized segment Anything Model 3 by 4.7 points on the Cityscapes benchmark, while operating in a zero-shot setting, which means the model is successfully generalizing across different visual environments with a level of sophistication we usually reserve for humans. Even more impressive is how the instruction tuning process preserves the underlying generative quality of the system, maintaining a 53.5% win rate against the Nano Banana Pro base model on text-to-image benchmarks, which suggests that teaching a model to see does not have to come at a significant creative cost.
I've been digging into the specific math behind how they actually map those unbounded metric depth values into a standard red, green, blue color space. And they are using a strictly invertible power transform with a lambda value of -3 to bridge that gap, which is a remarkably precise way to handle spatial data. The technical results are undeniable when the model records a 0.929 delta 1 score on metric depth benchmarks, using nothing but synthetic training data, which actually surpasses the 0.918 score from Depth Anything version 3, which is quite a feat considering they did not use any real-world imagery. It is quite a pivot from the days when we needed massive labeled datasets of real photos just to get a basic depth map working, because this demonstrates that if the synthetic data is high enough quality, the foundational model can learn the physics of a scene without ever having seen the physical world. While Google DeepMind focuses on perfecting how these models perceive the external world, other researchers are worried about the internal state of the system and how we must pivot from how models see the world to how they remember and compress their own reasoning history using tools like Microsoft OpenMementos for trace analysis.
Microsoft is introducing a new way to handle long-form reasoning through the OpenMementos dataset, which manages to achieve a 6 times token compression rate for complex tasks. This means we can pack much more sophisticated logic into the same limited context windows by condensing historical reasoning blocks into these highly efficient and structured mementos. By fitting these deep inquiries into fixed context limits, The system allows for massive scaling across math and science domains that usually exhaust a model's memory capacity. This ensures that the narrative thread of a complex scientific proof remains intact even as the model generates thousands of words of intermediate steps and crucial logical deductions. There is a real concern about the integrity of the training data during the supervised fine-tuning process, because if the parsing logic fails to align the block and summary counts, the traces break. When that happens, we end up training models that essentially hallucinate their own logic, undermining the reliability and the overall sophistication of the system. It feels like we are finally moving away from the brute force approach of just adding more memory and instead focusing on how these models actually organize their thoughts. Vance, how do you see the technical implementation of these specialized token schemas holding up when we move from general text to highly structured scientific data?
The use of specialized token schemas like the block start and summary start indicators is a vital step towards structured context management rather than relying on fuzzy attention mechanisms. It forces the architecture to segment reasoning into discrete units, which is necessary if we want to simulate inference time reduction by only retaining the last few blocks. I am looking at how they track median character and word ratios per domain to adjust the summarization density, because a one-size-fits-all approach will fail. The level of compression you need for a Python script is fundamentally different than what is required for a complex physics inquiry, where every single variable is critical for accuracy. We also have to be extremely careful with the data preparation pipeline. When mapping raw streamed rows into these structured message formats via the Hugging Face datasets library, any mismatch in those ratios or a failure in the parsing logic could lead to a catastrophic loss of information that ruins the reasoning performance we are trying to achieve. While improving how these models remember their own logic is a massive engineering win, we need to consider what happens when that logic is flawed from the start. We should shift from improving model memory to the security risks inherent in the code these models are currently generating for developers, like the Common Weakness Enumeration 1321. The core issue lies in how artificial intelligence coding assistants like Cursor and Claude Code generate deep merge helpers using the vulnerable for in pattern. This creates a Common Weakness Enumeration 1321 vector that allows attackers to pollute the object prototype through the proto key, which can lead to process-wide privilege escalation. Large language model training data is heavily influenced by Stack Overflow answers from 2013 to 2019, which prioritize statistically common but insecure historical patterns over modern safety. These tools are essentially repeating the mistakes of the past, because those patterns appear more frequently in their massive datasets than the newer and more secure methods. Exploiting these patterns in Node.JavaScript backends is dangerously straightforward. An attacker can inject properties like is admin true directly into the prototype during a configuration merge or through patch endpoints. This grants unauthorized administrative access across the entire application, because every single object inherits that malicious property by default, unless the code is specifically hardened. Even though a one-line fix using object has own entirely closes this prototype pollution vector, these artificial intelligence tools still default to risky for-in loops. This is why we see SafeWeave as a model context protocol server to flag these specific vulnerable patterns within our tools before they ever reach production.
Vance, your breakdown of those technical gaps makes me wonder if we are trading developer speed for a fragile foundation that hides old ghosts in new machines. It is deeply concerning that the reliance on outdated Stack Overflow patterns means our most advanced software is essentially hallucinating legacy vulnerabilities back into modern codebases that should have moved past them. We have to recognize that using specialized model context protocol servers to audit code is becoming the only way to maintain a secure software supply chain today. Without these safety layers, automated coding becomes a liability, especially when developers blindly accept deep merge functions for configuration loaders without performing a manual audit for inherited property guards. The human element of trust is being pushed to its limit as we integrate these systems deeper into our architecture. If we cannot guarantee that a basic merge operation is secure, it calls into question the value proposition of autonomous assistants that are supposed to make our lives easier rather than creating new security nightmares for our operations teams. This tension between the rapid generation of code and the actual security of the final product points to a much larger problem in the industry today. We need to move the conversation from these specific code vulnerabilities to the broader systemic reliability and governance issues that cause so many autonomous agents to fail when they transition from simple notebook prototypes to enterprise systems. The transition from a simple notebook prototype to an enterprise system is where most artificial intelligence agents currently meet their demise. We are seeing reports from finite artificial intelligence that engineering teams are spending up to 6 months just building custom infrastructure for observability before they can even think about a real production deployment. This lack of built-in audit trails is creating a massive bottleneck for security compliance. Startups are finding themselves stuck in service organization control to review delays ranging from 3 to 6 months. It turns out that if you cannot prove precisely why an agent made a specific decision, the auditors simply will not clear it. Because traditional deterministic unit testing is no longer effective, we are seeing a shift toward behavioral testing protocols. These require analyzing execution paths across 100 separate runs for a single input to account for the inherent randomness. Vance, how do the engineering metrics actually hold up when we scale these unpredictable systems?
The math behind these compound systems is frankly brutal for anyone concerned with uptime. If you have 10 individual agents each operating at a 95% reliability rate, your total system reliability plummets to only 60%. That level of failure is completely unacceptable for any mission-critical enterprise production environment. We are seeing a 63% variation in execution paths for identical inputs, which makes debugging a nightmare. This is why the approach of using a multi-agentic operating system to enforce identity management is so vital, requiring unique identifiers and full version history for every agent provides the governance that these systems desperately lack. Cost management is another area where standard practices fall short. We have to move away from simple session-based tracking and start looking at granular metrics. This includes measuring token cost, tool call cost, and the specific hop cost per agent run to understand where the budget is actually disappearing in these complex workflows. When you combine the reliability gaps with the high cost of each reasoning hop, the value proposition of autonomous agents starts to look very different. Without the architectural rigor of a centralized operating system to manage these non-deterministic behaviors, we are basically just throwing compute at a problem and hoping for a stable result.
Those underlying reliability issues become even more high stakes when we allow these agents to touch the core of our development process. We need to look closer at how we govern autonomous coding actors like Claude Code, especially when they are given the keys to touch production, continuous integration, and continuous delivery pipelines directly. Claude Code is not just suggesting lines of text anymore, but is acting as a fully autonomous production participant. It can execute shell commands and interact directly with our continuous integration and continuous delivery pipelines through the Model Context Protocol. This level of agency means the software is making real-time decisions that impact our live environment. We are seeing a phenomenon known as scope creep, where these agents attempt to fix unrelated bugs in the continuous integration environment just to unblock their primary task. While that sounds efficient, it often violates specific organizational intents and security policies. Without strict guardrails, an agent might rewrite critical configuration files just to make a test pass. The most terrifying scenario involves an agent merging a pull request into a branch with auto-deploy configurations. This can trigger an immediate system-wide outage before any human engineer has the chance to review the logic. We are essentially handing over the keys to the kingdom to a system that does not understand the business context of a failure. The integration of the Model Context Protocol is where this risk becomes truly tangible for the engineering department. This allows agents to access internal application, programming interfaces, and proprietary databases directly. Vance, looking at the architecture of these tool calls, how do we stop an autonomous agent from performing unauthorized write actions across our most sensitive internal systems?
Preventing those unauthorized actions requires us to move far beyond basic binary permission sets. We need granular tool-level policy enforcement that validates every single request against the current state of the environment. If we do not have a robust security layer between the model and our data, we are effectively giving a black box full administrative access. The danger is particularly acute when the agent begins touching infrastructure as code files. One unreviewed modification to a cloud resource configuration can lead to catastrophic downtime. We need a security framework that understands the difference between reading a file and modifying a production cluster. Relying on the model to police its own actions is a recipe for an immediate disaster. We must also implement a graduated trust model where human-in-the-loop oversight is strictly enforced based on the potential blast radius of the agent. If the software is just updating documentation, it can proceed. However, the moment it touches a production load balancer or a database schema, the system must halt and wait for a human verification. Managing these risks requires a massive amount of overhead that many organizations simply are not prepared for. It forces a hard pivot to the financial realities of scaling these complex systems on cloud infrastructure. We need to look at whether moving from Google Kubernetes Engine Autopilot to Amazon Elastic Kubernetes Service with Karpenter can actually slash our operational costs. That shift toward agentic systems makes the underlying cloud bill even more critical to manage. When you look at Google Kubernetes Engine Autopilot, you are paying for every millisecond of resources you request, rather than what you actually use. For a mature workload with steady traffic, that pricing model creates massive cost inefficiencies compared to more granular options. Moving over to Amazon Elastic Kubernetes Service with Karpenter changes the fundamental math of scaling. Instead of relying on predefined node groups that often sit idle, Karpenter monitors unschedulable pods in real time and provisions new nodes in under 60 seconds. It is a far more reactive and efficient way to handle the volatile compute demands of modern software. The real surgical precision comes from the consolidate after setting, which we can tune to just 2 minutes. This eliminates the ghost capacity and idle compute waste that usually plagues large-scale clusters. By constantly reevaluating whether a node is still necessary, we stop bleeding money on hardware that is essentially doing nothing but waiting for a request. Managing the complexity of spot instances is where the engineering discipline really comes into play. You have to implement simple queue service-based queues to handle node interruptions and ensure graceful draining of the pods. It is not just about cheaper compute, but building the resilient orchestration that allows a system to survive the sudden loss of a node.
Vance, that resilient foundation allows for even more aggressive hardware choices like the advanced reduced instruction set computer processors. Adopting these chips provides a clear path to better price performance for production services. We are seeing significant efficiency gains without requiring engineering teams to rewrite their entire code base for a different processor architecture. Security does not have to be sacrificed during this migration to more custom infrastructure. By utilizing Amazon Web Services identity and access management roles for service accounts, we provide precise permissions for every single pod. This eliminates the risk of shared credentials that often exists in simpler setups, while maintaining the high level of isolation required for sensitive data. There is also a significant networking hurdle to clear when moving from the Google Cloud Platform virtual private cloud native architecture over to Amazon. Redesigning subnet layouts is a requirement because of the fundamental differences in how these providers handle traffic. It is a complex transition, but the long-term financial benefits far outweigh the initial friction. These infrastructure optimizations are the foundation that allows those broader trends in artificial intelligence and vision models to actually scale. By driving down the cost of compute and improving reliability, we create the headroom for more advanced agents to operate. It brings our discussion full circle, showing that even the most innovative software requires a disciplined, cost-effective foundation.
We started with the efficiency of Google DeepMind instruction-tuned models outperforming segment anything Model 3. Then we looked at how Karpenter on elastic Kubernetes service can provision nodes in under 60 seconds to slash infrastructure costs. These are fundamental shifts in how we handle vision tasks and cloud orchestration at a massive, global scale.
Vance, seeing those advancements in high-speed orchestration and precision vision models, provides a clear map for where we are headed. Moving from experimental models to production actors requires a total redesign of our foundational frameworks. Whether it is using OpenMementos for context compression or reconfiguring cloud subnets, the goal remains the same. We are building the durable systems necessary for autonomous agents to function reliably and cost-effectively in the real world. As the boundary between human intent and machine execution continues to blur, the engineering choices we make today define the safety of tomorrow. Thank you for joining us on the Dev Journal. Until next time, keep building.